Quick poll. How many of you have ever trained a TensorFlow model or any machine deep learning model? Most of us have. How many of you have run that in production or served it in some production setup? Okay, that's less. And this is basically what this talk is about. How can we move from the training part to like a real production pipeline of deep learning? I'm Jörg. I'm a technical lead at MESOS, where I'm responsible for community projects. That means I deal with all those projects which product doesn't feel, or which product isn't taken care of, including TensorFlow, including Kubeflow, and all those other tools. And if we talk about deep learning, so this is currently there are a lot of blog posts, a lot of talks also here at this conference. So why is it so popular? What is the promise? The promise is that actually traditionally we had this data scientist sitting there and he had the task to classify, is this a dog or cat? Is this a hot dog? Is this not a hot dog? And so what he would do in traditional machine learning, he would go in, he would collect some features from those pictures, and then with those features use a more traditional technique like SVMs or others to actually classify whether it's a dog or not. In deep learning, we're kind of replacing this manual feature extraction part by just more compute power and more data. So we're replacing this person, he's still needed, but the core part of feature extraction is actually put up onto the machine, and there we can avoid the biases, because one of those engineers, they typically have biases in which features they select, and the deep learning powered by machines is actually just about data, so they'll select the best features for that data set. So how does it look in production, the process? We typically have lots of labeled images. So we need a bunch of images where someone has gone in and tagged, this is a dog or this is not a dog. And with those pictures, with this training data, we actually go in and we train our deep neural net. And this means that we adjust the weights during the training process until this neural network is actually able to predict whether this picture contains a dog or not, and at best it's also able to predict this bounding box here. So the output of the training is actually a trained model, and then the second part in which we use this trained model is typically referred to serving or inference. And so here we use our trained model with previously unseen images, and then we use our model to predict whether there's a dog in there or not. So this is basic overall process here. How does it work? So what's kind of the intuition? Why does that work? Just throwing a lot of compute power on those pictures and then being able to extract all those features. And so this is, if you recall here, those models, these deep neural networks, they have different layers. And our intuition is that different layers are detecting different features with increasing complexity. So the first layer in our network, they are typically able to detect very simple features, such as lines, circles, or something very basic. The next layer in the picture is then making use of those previously detected features, and they can actually assemble them, and they're able to detect, is this an eye, is this a nose, is this fur? And then the further layers in the image, they make use of always the earlier layers, and they are always able to predict more and more complex features. And at the end, our final layer is actually able to detect, is this a dog or is this not a dog? So what is the challenge we are facing? I find, especially TensorFlow, it's very, very easy to use on my laptop. I simply download this binary, I set it up, and I can easily train a simple model for MNIST, or if I'm using a pre-trained model, I can even do this dog, non-dog classification. But what does it mean to actually move on towards a more production setting? Like on a laptop, I don't have that much compute power, and probably I can't train very big models. How many of you have heard of Kubeflow? 1, 2, okay. So Kubeflow is a project for machine learning, deep learning on Kubernetes. And so what it's using, it's kind of like a small stack. So I get a Jupyter notebook. A Jupyter notebook, we'll see that in more detail in just a second. It's basically a way of enabling us to have a very simple interface where I can edit my model, where I can play with my model, and then I can also just run this model. So like a web page where I can develop my model. Then I have TensorFlow in here, which is being used to train that model. TensorBoard is a way of monitoring the progress of my learning. So there I can see like what is the current accuracy already during while it's learning, and I might abort because I'm seeing that it's pretty bad, for example. And then there is debugging. So TensorFlow debug enables me to debug this graph structure and figure out where I might have to optimize my model or where I have gone wrong in specifying my model. And then the last part included in Kubeflow is TensorFlow serving. So that's a way of enabling me to actually serve this model after all. So this seems like a pretty good data science pipeline, right? But unfortunately, we even need more than this. So if we are moving to a production setup, typically what people do with Kubeflow, they are running on Google Cloud, AWS, or some kind of cloud environment. And this is actually enough having all of this, because we get for free stuff like storage, we get something to do our data preparation, we get a streaming abstraction, so we kind of can use all those cloud abstractions. Unfortunately, this doesn't work well if we are in an on-prem setting, and there we actually might need other tools. So in an on-prem setting or in a general setting, if I don't want to commit to those libraries, to those proprietary solutions from the cloud vendors, I typically end up with something like this. I'm using Spark for data preparation. I'm having a distributed file system such as Hadoop HDFS, for example, for data storage. And then I'm having Kafka if I want to have like streaming requests. So later on for model serving, how do I actually get all those requests to my model? And their typical abstraction is to use a message system, a message queue, such as, for example, Kafka. And with that, I can actually build an entire deep learning pipeline around Kubeflow. So if we want to see that more general, so those were just a few instantiations of deep learning pipeline, what do we actually need to build a complete production-ready deep learning pipeline? And so it starts with the data and streaming. So how can we manage all our data in the system? The second challenge is then, what is the interface to our users? So those can be Jupyter notebooks, this can be Zeppelin, this can be Spark. So how do the users interact with the cluster? Then TensorFlow is just one of the many tools which people might use. So there are other tools such as PyTorch, MXNet. So you actually have to choose one of those deep learning frameworks to use in your architecture. Or you can even choose multiple if you want to. Then you also need a cluster where to run all this on top of, and some kind of management system to manage this. And Kubernetes, we just seen for Kubeflow, is really great at managing containers. There's yet another abstraction which is called Apache MESOS, which is an open source project which really aims at abstracting away clusters and enabling us to run all of this on top. And we'll see that in more detail. But the next step in our pipeline is then actually the model handling. What we should keep in mind is that in this pipeline, we are not training a single model. This is a very iterative process. We are training hundreds of models because there are different hyperparameters, there are different data sets. So our data set, our training data set might grow over time, so we need to retrain. We are changing some parameters. So we actually end up with a bunch of different models. So we also need a way to store those models and the associated metadata. And then if we really want to use it, we also have to do model serving. So we kind of have to put this model to good use and serve it and then use it for some kind of production workload. As this is quite a complex pipeline already, we should monitor that. And monitoring should be done here at 2 different layers. So first of all is actually monitoring this entire infrastructure. So all those different systems, you see we don't end up with like a single distributed system. We're actually combining multiple distributed systems. So we should have something good to monitor that as, for example, Datadog. The second thing we need to monitor are our models themselves. So while we train them, we already talked about TensorBoard. I need a way of actually seeing what is the accuracy, how do they compare to other models, how is the error rate, for example, dropping during training. So I also need some deep learning specific monitoring tool. Okay, so the training challenges. This training, it's very compute intensive. And as mentioned, it's not a one-time instance. This is actually very iterative because first of all, it's compute intensive because we have hopefully a lot of data. So the trained data set should be rather large so that we end up with good models. After all, we are replacing this human being which extracted the features by data. So we need enough input and training data here. The second challenge is that we actually need to find the best network with the best hyperparameters. So there are questions, how many layers should I choose? How many units should I have per layer? What is the learning rate? So how quickly do I want to change my weights? And all of those are actually hyperparameters. And for different hyperparameters, I may end up with very different performance and with also very different generalization of my network. So typically what I do, I'm not training one network, but I'm training a bunch of those somewhere in the realm. If I have a large hyperparameter space, it's often like several hundred networks I might end up training. Okay, and so what we'll do now, we'll actually just go through this pipeline and look at the different stages in some more detail. And as it's all about the data, we'll start with the data stage here. Input data management. As we just said, we have a lot of input data, hopefully, so we have to manage them. The second challenge is that typically we have to worry about quality of this data. And so if we go in, the first thing we typically need to do, unless we have a nice demo data set, is actually some data preparation, data cleansing. So we have to look at, are there missing values? Can we refill those values? Can we kind of infer them from other data? Or do we actually have to delete the entire record? Then incorrect labels. Do we see that like some labels are obviously incorrect, and we should also handle those. Also, we should get all the data in the same format. And the trivial things are, for example, they should all have the same time format. They should all have the same units. Like in IoT use cases, I might end up with data. Some is in miles, others is in kilometers, metric system. So I actually need to harmonize that data. And then another trick, which is often done to make it easier to deal with data, is to kind of bring it all in the same distribution, which makes data more comparable. So my input data from in different dimensions is actually comparable in distribution, which makes the learning process and progress much faster. And so this is a very important challenge in input data management, and we should really not forget about that. Because what I see in production use cases where people spend time, it's typically about 50% at least on the data preparation, another 20% maybe on the data serving in the end, and then it's only 30% of training the actual model. So it's very important. And typical solutions for input data management are HDFS, GFS if I'm in a cloud environment. I might use Kafka if I have streaming data coming in. Kafka also has a persistence layer, so I can even use it like a database. If I have more structured data, I might also use something like Cassandra or Redis for more document-like storage. In terms of data preparation, I guess the most common tool is Spark, which is what most people use to clean up their data in a batch. If people have streaming data coming in and they can actually define that as a streaming job, I also have seen some people using Flink for cleaning up their data. Next part, the user interface, the user interaction. Typically, if we look at the stack, it's addressing different users. First of all, there's a data scientist who might want to explore the data, who might want to come up with that model. And depending on how large the team is, there might be yet another person who is then training the final model on like a large distributed setup. And there's at least one infrastructure engineer who is taking care of coming up with this entire pipeline. So if I'm a data scientist and I'm only concerned about the data, I don't even want to have to look at the rest of this. I only want an easy way of interacting with the data and being able to train my model. And so there, Jupyter notebooks are a very useful tool. It's like here, it gives me like a web interface in which I can go in and I can specify my Python code, and then I can launch this Python code from this web interface. So this makes it very easy to explore my data set. There are extensions to Jupyter Notebooks, and one I like quite a lot is called BeakerX. It gives me JVM extensions. It gives me nice export functionalities. So export functionalities, this means if I'm done specifying my model here, I need to export it somewhere to be able to train against a larger cluster. So it has capabilities for that. Other people, they're using Zeppelin. So traditionally, Zeppelin has had better support for Spark, whereas Jupyter is kind of more focused on this TensorFlow deep learning area. But the recent developments are actually quite converging in terms of functionality. So it also comes down to taste. From an ecosystem, probably Jupyter has a larger ecosystem and a more vibrant community right now. Frameworks and clusters. So if we just look at what has been happening to the TensorFlow community, this is the number of GitHub stars. So we see after Google put TensorFlow on GitHub, it's really been shooting up and kind of taking over all the other deep learning frameworks such as Caffe, deep learning, MXNet, and so on. We can discuss whether GitHub stars are a good metric, but it's one metric, and most of the other metrics are going in a similar direction that TensorFlow currently is getting a lot of the hype in the deep learning area as a framework. But there are actually also other tools. So what is this framework actually? So TensorFlow is a library which enables me to do machine intelligence. It's mostly used for deep learning, but it can also do other stuff. But what it's really good at, it allows me to specify this network and then train this network across the different environments. So once I've specified it in TensorFlow, I can train it on Google infrastructure with TPUs. I can train it on my own cluster. I can train it on my own machine. So this is kind of the functionality, the abstraction I get here. So I write against this library, and then the rest of the actual executing code is being generated for me, and I don't have to worry about what kind of features my CPU supports, whether there are GPUs available. TensorFlow will take care of that. But as mentioned, there are also alternatives. So one thing which has been a critique of TensorFlow is the way that I have to specify a static compute graph. If we look at this is a very simple example. What I have to do in the TensorFlow example, I first specify the entire graph. So you see here, I'm setting those placeholders, I'm setting my cost function, and so I'm specifying the entire graph. And then with tf.session I say, now train it after I've specified it. PyTorch, on the other hand, has a slightly different model, which is referred to as dynamic compute graph. So there we can see in this range loop here, so where the actual work is being done, this is where we also construct our graph. And constructing this graph while we are executing it makes some things easier. For example, debugging. I can simply throw in a print statement in this loop and output my debug information. This is harder here because I've specified the entire graph, and then it's just being abstracted and executed by the TensorFlow library. On the other hand, the static compute graph actually gives me advantages because I can do more optimizations because I have the entire graph. So TensorFlow can optimize across the entire graph. And also TensorFlow, the TensorFlow community has picked up on this criticism, and they included in the 1.7 release feature. It's called Enable Eager Execution. And eager execution basically lets me do the same thing as with PyTorch, where I can build a dynamic compute graph on the fly. The entire ecosystem is even much larger. So there's PyTorch, there's MXNet, there's Caffe, and many other tools. And so the question is, which one to choose, how to deal with that? What I often see is that different teams are actually choosing different solutions, even though they're in the same company, in the same overall project, because different frameworks tailor different needs and make it easier to solve specific problems. Even if we're inside TensorFlow itself, we still have a lot of choice of how we want to interact with TensorFlow. So how many of you have started using TensorFlow about like a year ago already? Okay, some. So there we actually were mostly here at those low-level APIs. And with those low-level APIs, you actually have to specify which devices you want to use, how to set up your graph and everything. Since then, we have higher-level APIs. So what I would really recommend if you start using TensorFlow right now, try to start using the estimator API and then the dataset API for accessing your data. And this will make your programs, your models much more portable, as you don't have to worry about how many nodes it's running on. The estimators will actually do most of the magic for you and try to optimize it. So only in cases where it's really hard to write your own estimator, you should go to those low-level APIs and use them. There are also a lot of so-called pre-canned estimators. So if you have a common problem such as image recognition, sentiment analysis, translation, they're actually pre-canned estimators. So you can just use them. You don't even have to train them, as Google, for example, provides them for you. And Google has trained those with about like 200,000 TPU hours, which is an equivalent of like at least $100,000 to $300,000 of value. And you can simply reuse that, what they've invested in training those models. Okay. The second part we should look at is then the cluster management. The challenge here is we have a lot of tools running, and we need some way of actually orchestrating and dealing with all of those. So if we are on a single node, also we don't have to deal with a cluster. I simply download the binaries and run it. But if I'm in a distributed environment, it already becomes more complex, because I have to go in. I have to provision TensorFlow on all those machines. I have to write a so-called cluster spec, matching those IP addresses where everything is running. I have to deploy my code across all those instances, and then I can finally train my data. And so setting up this distributed setup is also challenging, because we end up having different components. If I'm running on my single server, it's just like this one TensorFlow instance. But if I'm running a distributed TensorFlow setup, I have at least two different types of nodes. So I have worker nodes, which are doing the actual computation. And then I have parameter servers, which are being used to exchange the information about weights between different workers. So kind of like communication and storage servers, if you want it this way. And when setting this up, I actually have to decide how I want to configure my cluster. Second thing is, if I'm running in a cluster, I actually have to take care of resource isolation. If I'm only running one TensorFlow framework, that's easy. But if I'm running multiple of those, if I'm having multiple users sharing that cluster, I have to deal with resource isolation. So I might end up having all those frameworks fight about access to like a GPU, for example. So how do I do resource isolation and the allocation part to the individual frameworks? TPUs, same problem. As of right now, they are only available in the Google Cloud, so it's kind of an external resource I might have access to. How many of you know TPUs? So I hope GPUs, like graphic processing units, is kind of a term. So TPUs is a tensor processing unit, and so that's a piece of hardware which has been developed by Google in particular for machine learning and deep learning. So it's really good at vector and matrix operations, and so really tailored to this problem of training large, deep neural networks. And in Google, they have pods of those, so there are a bunch of those inside one of those racks here. Okay, what does it mean for our data center? So if we want to implement this entire pipeline in our data center, we have all those different frameworks. We have Spark for data cleansing, we have TensorFlow for learning, we might have a different TensorFlow for yet another team. If we set up a CI/CD pipeline, we might even have Jenkins in there, Kafka to have our message queues. So we end up with a lot of different distributed systems which we want to deploy on this cluster. And the traditional approach, which might work in a cloud environment, but even there I'm wasting a lot of resources, is I go in, I pick the first 5 nodes, and I install Spark on them. I pick the next 10 nodes, I install TensorFlow on them, and so on and so on. So I kind of statically partition my cluster. And this, first of all, it's a lot of operational effort, as someone has to go in and partition this cluster. If there are failures, this person has to go in and repartition the cluster. And on the other hand, I'm wasting a lot of resources, because in each subcluster, there are some idle resources. So the idea of this open source project called Apache MESOS is to actually view your entire data center, so all these nodes as one big pool of resources. So I'm not saying deploy Spark on those nodes, but deploy Spark with those resource requirements. And so it's similar as with my laptop. My laptop has multiple CPUs. I don't care which CPU is currently being used to show this presentation. I simply want that it's being displayed on the screen. And so that's similar with the abstraction MESOS gives me from my data center here. Then Mesosphere has built something called DCOS, so the Data Center Operating System. And this is being built around Apache MESOS. And it kind of gives me, first of all, security, monitoring. It gives me an app store from which I can install TensorFlow and all those very easily, databases. And also, as Apache MESOS gives me this abstraction layer from the resources, I'm actually independent on the infrastructure I'm running. It can be in an on-prem cluster, it can be in an on-cloud cluster, but I'm not tied to any specific vendor-specific APIs. I can easily migrate, and I can even work between an on-prem and an AWS data center if I need to extend and burst my cluster into the cloud. Okay, coming back to TensorFlow. So even though we have this cluster problem solved now, how we can throw all this on a big cluster, I still have to be able to run and deploy it. And as training a large model might take up to days, sometimes even weeks, there will be failures in between. So nodes might fail, and with this hard-coded cluster spec, recall this cluster spec is where I put in parameter service is running on IP X, worker is running on IP Y, and so on. So if those systems are failing, it's actually very annoying to recover from that. And especially if I'm the administrator, I'm being woken up at 3 a.m. at night, and I have to deal with that something in my cluster is failing, that I have to scale the TensorFlow job because it's too slow. It's actually really annoying. And so this is the second feature of Apache MESOS, that we have the so-called two-level scheduling architecture. So we actually have like a small so-called scheduler, which is encoding all this lifecycle management for the TensorFlow job. So it restarts stuff, it deals with failures, it allows me to change configuration, to, for example, extend my cluster if I'm needing more resources, or to also remove nodes if I'm having too many. So this is actually then very specific to this framework. So I'm having one scheduler for Spark, I'm having another scheduler for Flink, another for Kafka, and so on. So with that, it actually makes it very simple to maintain a TensorFlow cluster in a distributed environment, because I have this supervisor, this operator component, which is actually monitoring this cluster and always trying to deal with failures happening to that cluster. Okay. Next part, models. So as we said, we're training a lot of models, so we actually also have to store and keep track of them. So here, this is an iterative process, and we end up with a lot of models. And so what do we need to do? We need to store two different parts. The first part we need to store is the model itself, so this graph structure. The second thing we need to store is the metadata associated with that. So what is the accuracy? What is the performance on various test data sets? Which model is it actually coming from? So if I'm having this model stored, it's always good to have like a trace back to this original file, to this Python file I used. So it should actually also be stored in a version storage. And so what I'm seeing there is often distributed file systems such as HDFS or GFS. If I'm in a cloud environment, they're being used to store the actual models, so this graph structure with all the weights. And then I'm having typically a document store such as MongoDB or a RangoDB, which allows me to have a document store plus a graph store to store the metadata. How many of you know TensorFlow Hub? 1, 2, 3. So TensorFlow Hub is actually, they just announced that, I think officially, at the TensorFlow Dev Summit last month. So this is a nice way of actually getting models which have been pre-trained by Google. Imagine you're doing a very common task. So this is about word embeddings. So how do you convert words into an embedding describing this word, which can then be better used for translation or also just understanding what's going on? And Google already has trained a lot of those models on a very large scale, which we cannot even afford ourselves. And so they've come up with TensorFlow Hub, where anyone can contribute models to, so pre-trained models, and other people can simply use them. And the way in which we can use one of those trained models is typically we download that model, we use everything up to the last 1 or 2 layers, so we delete the weights in the last few layers, and then we retrain it with our own specific data set. So those last layers, they actually get trained to our particular data set, to our particular problem, while the overall structure, for example, image recognition or translation, is rather independent of that. If you recall, this initial insight in how it works is that the first layers, they're detecting more general features such as lines, circles, and so on. So this is actually the same for all models. And then the last layers, they're just assembling those high-level features to come up specific to your data set. And this is why you only have to retrain the last layers in your model. Okay, serving. So once we have trained our model, we actually also have to serve it. And often I need an architecture, whether I'm using TensorFlow serving or not. Often I end up with an architecture which is pretty similar to TensorFlow serving. So how does it work? I'm having some store. So for example, watching a file system. And whenever I'm adding a new model, this gets automatically loaded by the loader. And then there's the version management. As said, often we have multiple versions of a model, and so we now have to decide which ones we actually want to use if a query is coming in. And so this is done here in this dynamic manager. With a version policy, we can define which model should actually be used. And then when a client sends a query, he gets a response from the output of this model. TensorFlow Lite. So different models. I might have different models for different use cases. So TensorFlow models, they often end up having 80, 100, or even more megabytes, and running this on a phone is pretty prohibitive. First of all, because it's too large. Secondly, because it also simply takes too long. So there's a project called TensorFlow Lite, which is compressing that model to somewhere between 300, 500 kilobytes. And first of all, this makes it feasible to download it to a mobile phone or another embedded device. And secondly, it's also running faster as I'm having less work to do. So this is pretty handy to have different versions of your model and available for different execution platforms. Another platform or another architecture which often is used, so this is, has been proposed by Ted Dunning, is called the Rendezvous Architecture. I've seen different derivations of that, but the central idea is that we're not using a single model to serve our data, but we're actually using, like in this example, 3 of them. Then we're having an input queue, so typically a Kafka pipeline, and all models are getting the same request. All models are computing and trying to serve this model. And then there's an output Kafka stream, which is collecting all the scores, and the rendezvous part, which is then deciding which score wins. So it can either pick the best score according to some metric, or it can also do like a majority decision, for example. And this result then gets back to the client querying that. Monitoring. So as mentioned, this is a very complex setup, so we also have to do monitoring. One of the most important parts, and probably I as a data scientist, I don't necessarily care about doing monitoring on this entire infrastructure, but I as a data scientist, I still care about looking at my monitoring performance. So their TensorBoard is a very useful tool because, for example, like here, it shows me certain metrics already during the training progress. And this can also, for example, allow me to do early stopping or to keep on going and figure out maybe this model is not so good. I still need to come up with another one. So it kind of keeps track of model quality. And then if I'm more into infrastructure, I actually want to make sure this entire pipeline is up and running. I'm having decent cluster utilization. I'm not wasting too many resources in my cluster. And everything is up and running and healthy. Debugging. How many have used TF-debug? No one. OK. At least I'm seeing no hands. So what makes debugging TensorFlow really hard is the static graph, because it's compiled into this graph, and I cannot simply throw in a print statement somewhere into my graph. So I need more advanced tools, and probably TF-debug is kind of the default tool to actually do that. They recently, this is just in beta, they also integrated that into the TensorBoard, which makes it nicer, right? If it's integrated here, it's more visual, and I'd always prefer this over this here. So that'll actually make it much simpler, but currently this is just an alpha, or I'm not sure whether they already have moved up to beta for the TensorFlow, for the TensorBoard extensions for TF-debug. What you should keep in mind, it's debugging not only refers to getting the correct or expected result, as usually you don't even know what that is. It's typically when you're debugging, you're trying to optimize the cluster usage. So what I'm most of the time looking at if I'm doing debugging, like how utilized are my GPUs? How can I optimize my code that actually my GPUs are being busy all the time? Because that's what I'm paying Amazon a lot of money for, that I'm getting a cloud instance with a GPU inside. And this leads us to profiling, which is also like the extension to debugging. So this is probably very helpful and to learn. It looks complex here, but if you spend some time with it, it's actually very easy to understand where your time is being spent and how your data flows. So why is the GPU not utilized? Platforms, -1. I have 1 minute. So the obvious question now is where can we deploy those pipelines? We've seen Kubeflow early on, but there are others. Like all cloud providers, they have their own pipeline. AWS has SageMaker, which gives me a lot of different tools. Google Data Lab ML engine is also rather nice. Kubeflow I can deploy on any Kubernetes cluster. And then what we talked about with Apache Mesos and DCOS, it kind of gives me the most flexibility, as I can go in any environment, I can deploy anything I like, but it also requires more manual setup, as it's not like a managed service hosted in the cloud, but it allows you to actually build your own managed service. Related work, just check the slides later on, as I'm running out of time. And actually, thanks to all the collaborators, there's a large community driving this, especially also on DCOS. So this is really cool to see that there's a vibrant community driving that. And if you feel you want to contribute, just come in and submit a PR. And otherwise, thank you very much for listening. Do we have time for questions? Or yeah. So, in your opinion, what are the reasons for terminating and restarting a model? I assume this question is meant for while we are serving, so when I want to switch over to another model. And there can be multiple reasons. First of all, I might have gotten more training data, and so I have a better model. I might have even explored different hyperparameters, so I might just simply want to use a better model. Secondly, over time, if I'm dealing with live data, I might actually end up that my input data, my requests are changing. So the distribution in my request is changing. So the model I've used before might not be applicable anymore. So if you recall this rendezvous architecture, a typical pattern there is also just to monitor the distribution of incoming events. So for example, if for the last 3 months you always had 90% of yes answers, and all of a sudden you end up only having 50% of yes answers using the same model, then probably you should look at whether something has changed in your input data, and then you might want to use a different model for serving. Any other questions? Otherwise, I'm around. Just feel free to come by and ask other questions. Thank you very much.